So next up we have Nick Slabakov from Juniper, Source Routing 2.0, why now, why again? Nick.
Good morning, everybody. So let me start with a question. How many made it yesterday to the Facebook NetOps coding tutorial? Yay. Wow, seems like most people. I enjoyed it a lot too. What a great job by Facebook to tell us about their F-bar system that allows them to pretty much run their network without a knock. I think they said like one guy is on call. What an awesome job by David Swafford for keeping about 500 of us on track for 3 hours, writing Python code at the end. Even I wrote something, and now I get to wear a T-shirt with some Python stuff on it. Seriously though, what Facebook did is they took a fairly old technology. I had to look it up last night. Python has been around since 1989. I think that's the year when the Berlin Wall fell. They've taken a fairly old technology, they've added some new insights to it, some pixie dust, shall we say, and have developed something that's pretty cutting edge. I'll say the envy of many. I looked at the age of Python, and then I thought, few technologies out there are as old as Python, and source routing is one of them. So we'll talk about source routing today, again, from a perspective of some new ideas, some new insights that people have added to it in order to do cool things. The way we're going to do that is I'm going to go through a little bit of history of source routing, level set everybody on what that is. But the real reason for talking about source routing today is the resurgence of, or the emergence of this segment routing technology, which uses the concepts of source routing. So this is not going to be a segment routing tutorial by all means. There are better ones out there. All I'm going to do is just kind of mention a few major concepts just so that we all understand the insights that came out of it and got implemented by some people. We call them spring inspirations, by the way. So first, a little bit of a level set. I'll use these three terms fairly extensively in this talk. Source routing is a very generic term. It's been there forever. It basically covers all these technologies that allow you to put a prescriptive header in the packet and send that packet in the network, and every router acts on that prescriptive header with regard to its forwarding. Segment routing, on the other hand, is a specific incarnation of source routing. It's kind of the technology du jour, shall we say. It kind of does the same thing in a particular way. Spring is simply the name of the IETF group chartered with standardizing these source routing technologies. I will use the Spring term and the segment routing term pretty sort of interchangeably in this presentation, and most people do that anyway, and it's okay. So the main idea back to source routing, the kind of the generic thing. The main idea there is let's prescribe the path of the packet in the header of the packet itself, and then launch that packet into the network, and each router acts on that header, and that header tells them how to forward that packet. A nice side effect of that is that you get to avoid loops in the network quite easily by just describing where packets go and eliminating the hop-by-hop decision from routers. Another nice side effect is that you get to reduce the forwarding state in the network, which is always a good thing. A few historical examples. If you guys come from high-performance compute environment, there's all these exotic interconnects there, Spacewire, Marinette, they all use source routing technology in their forwarding. Those of you that are of certain age will probably remember token ring and APPN and all these other technologies that also use source routing in their core. But for most of you, source routing probably means putting source-routed headers in the IP packet. And V4 and V6 both have definitions for that. Unfortunately, all of those definitions have been, kind of deprecated. That simply didn't work out. And you would think that V6 will get it right, but it really didn't, leading to RFC 5095 pretty much banning routing headers from the packets. Tunneling, on the other hand, if you're in a service provider edge, and if you take a packet and put it in a tunnel and then source route that tunnel packet, that tends to be treated with better respect and considered more secure. In fact, all of these MPLS networks today, that's what they do. If you're familiar with RSVP, it uses EROs, and EROs are nothing more than source-routed, statements. So why now are we talking about source routing again? It is because of the industry interest in Spring or segment routing technology. Again, the key in Spring is to tunnel packets from the source to the destination by describing the path of the packet in a header with a sequence of segments. That's what segment routing is calling it. And there's certain good flexibility there. You can describe more or less in the header, depending on how much you care about the specific path the packet needs to take. The other reason why this new interest in source routing has come around is the resurgence of the interest in centralized controllers. And they are not a new idea by themselves, but with all the interest in SDN, of course every SDN has one of these, or more. Their job is generally to do path calculation and also path imposition at the ingress of the traffic. And the ingress could be either a host or a router, but the confluence of those two factors has started people thinking again about, hey, what can I do with source routing these days? So I'll go through a few slides only. Again, just a couple of concepts around Spring. Nothing inclusive, really. There's much more extensive tutorials out there. There are two main concepts around Spring. One is, or segment routing. One is that every router is going to assign a label to all of its interfaces, and as a matter of fact, to its loopback address as well. And it's going to flood these labels into the IGP. And with that knowledge, every router now can craft a packet by creating a label stack and putting it on top of that packet, and that label stack pretty much describes a sequence of links in the network of how that packet should be forwarded. So that's pretty clear, pretty sort of conceptually nice. Spring defines two major types of segments or labels. The first one is this adjacency label, and it's again pretty simple concept. Every router assigns a label to each of its adjacencies, or its neighbors basically. And the interesting labels here, I have them in red. If a router, say R1, wanted to send a packet to R5, all it needs to do is craft a header for that packet that kind of looks like this, with label 2 or 3 on top. And that label 2 or 3 was announced by the next hop router, router 2. And that label meant, hey, if I get a packet with that label, I'm going to forward it. I'm going to pop it first, and then I'm going to forward it to router 3. And then router 3 is going to receive a top label of 307 and do the same thing. Router 7 is going to do the same thing until the packet header dwindles and the payload of that packet ends up in router 5. So we just source routed that packet. A couple of observations around this. There's certain goodness that comes with this kind of source routing the packet. You're reducing the state in the network. You no longer have to have end-to-end LSPs. Instead, each ingress can simply describe the path that one wants to take. and doesn't have to actually refer to an LSP for that path. Then again, if you are relying on things that rely on per LSP state in the network, such as bandwidth accounting, such as traffic engineering, you may lose some functionality if you just do this type of forwarding. The other observation I have is that it's a trivial method of forwarding in a way that you need to expend quite a few labels in the packet in order to describe the path of the packet. So that doesn't come for free, either on merchant silicon or custom silicon. You know, there's some cost associated with pushing these kinds of deep label stacks. And the third thing is that you almost never really care to describe the packet with this level of specificity. So enter node segment, or node SID, or node label, all the same thing. Pretty fundamental and quite powerful concept in Spring, which calls for each router announcing itself, let's say the loopback address, its own loopback address, with a label that is globally known to everybody in the segment routing domain. This is very cool because everybody now should use label 107 in order to send packets to router 7. It's cool because I know what that label is, and that's useful for troubleshooting if I want to integrate a controller or whatever. Now, the only problem with that is it breaks interoperability, and it breaks it in at least two major ways. So one of them is that if some router from this network was actually connected to another labeled domain, say RSVP or LDP, it may have already allocated that label 107 for that protocol, for that other protocol. So it may not be able to comply with the demand here to use label 107 to reach router 7. So that will break. The other thing is that it breaks interoperability between vendors, because if this was a multi-vendor network, you would need to get all the vendors to agree that label 107 is dedicated for this purpose. Well, some labels managers may have chosen to already allocate that label to some other purpose. So you can't assume these things, if you wanted to achieve interoperability. So time doesn't permit me to actually go through the workaround and the solution for this problem. I do have a backup slide at the end of this deck that you can kind of walk through, and it describes how Spring solves this problem in terms of implementation. But the concept is there still, that you have a globally unique address that you can use for your destinations. Last thing I want to mention is Spring has the notion of a label stack compression, and that's basically the combined use of adjacency labels and node labels in order to achieve reduction in that overall size of the label stack. Again, we kind of established that that was a good thing. The top example shows you simply using adjacency labels, and you're going to need 4 labels in that stack. And then if you combine it with a node label in the bottom example, you can reduce the label stack size by at least 1 label. Okay. Seriously, last thing on segment routing. This is just mostly for completeness. You will probably encounter a bunch of other segment types, which fundamentally are really similar to the first two that I mentioned, the adjacency and node. But they're used for different use cases. So there's peer node, peer adjacency, and all that. You'll also probably discover discussion about mapping servers, which help in achieving interoperability with LDP. You'll also probably discover discussion about SID TLV mapping, which is helpful for achieving interoperability with RSVP. And lastly, you'll probably discover a discussion about incorporating segment routing into BGP, which is the sort of the de facto protocol for most large data centers. Okay, getting to the main the main points that I'm trying to make here. First, the two main insights that come out of this whole Spring discussion that I wanted to bring out were this. There's certain goodness in having predictable label values, especially for your destinations. Well, that's what the destination IP does. It has a predictable label value, except if we're tunneling the packet, there's also value in the tunneled packet itself having a predictable destination, which is the label value. It's good for troubleshooting. It's also good if you wanted to incorporate a controller in your network, or if you wanted to source these packets from hosts that don't speak network routing protocols or label distribution protocols. So for all those reasons, there's goodness in predictable label values. So we want to achieve that even in environments that are not Spring or segment routing environments. And then the second sort of idea is the notion of this node SID. There's certain elegance in being able to address a node with one simple instruction from the ingress all the way to the egress, and not have to care about how to route the packet through a network. The node SID basically allows for the packet to get to the egress over whatever ECMP path is available to that egress. So again, people have looked at, can we do these things without actually having to upgrade our network to Spring, which is a fairly large exercise. At a minimum, it's a software upgrade. It also involves a completely different way of forwarding, so your operational staff needs to understand that. Who knows? It might even include some new bugs. So this is a fairly commonly referenced use case for segment routing for Spring, and there's a special draft that describes it. Kind of in essence, the idea is that if I wanted to exercise every path in a network with OEM probes, I can just craft these OEM probes and use adjacency segments or a combination of adjacency and node segments to steer the packet every which way I want. Segment routing lends itself really well to that sort of thing. There are some enhancements toward that. At the bottom I have this aggregated bundle, Ethernet bundle. I could assign segments to the bundle itself, but I could also assign segments to the constituent links or the child links in that bundle and exercise predictably those links, which is kind of a cool idea too. The segment routing approach to this would be, I craft a packet like this, and this packet says, hey, traverse that ring in a clockwise direction, and in this particular stack of segments, I don't care about which link of the bundle I exercise, just go ahead and use the vendor's load balancing algorithm, and the packet gets through. Now, if you do care about which link you exercise predictably, then you can make a slight modification to that stack, and the label next to last here is now 4011, I think, or 4031, which causes this packet to be steered through the top link in the bundle and exercise that one predictably. And then lastly, using that concept of stack compression, if you don't care about all these specifics and if you wanted to just exercise a link, you can say things like, hey, get that packet to router 4, and then just exercise the top link in that bundle and then get it back to the path management server. So lots of flexibility there. Turns out you can do these things in other ways, and people have done them in other ways. My first example comes from Google, who presented this a couple of nanogs ago. What they've done is they've created a fairly exhaustive mesh of RSVP LSPs, and they have injected probe packets into those LSPs, and then they've collected those probe packets and analyzed them and made sense of them, which links are failing and so forth. Now, the only drawback with that solution is that in doing so, they've also created a full additional RSVP mesh, which creates a lot of extra state in their network. So other operators have picked up that idea and kind of moved it on borrowing a couple of more concepts of segment routing, except they have done it also without segment routing. They've done it with static LSPs. The beauty of doing it with static LSPs is that you don't have to install any kind of control state and very little per LSP state in the routers. So these are kind of config snippets and examples of how this would work. If you were to craft a packet like this one in the bottom and inject that packet into R1, R1 is going to act on this top label of 1,000,002. And that top label, based on the configuration there, says pop the label, and then send that packet to the next hop of 1112, which happens to be router 2. Router 2 has a similar configuration that would act on the next label in the stack, 1,000,003, and then it's going to send that packet to R3. R3 is going to act on the next label, send it back to R1. And R1 is going to look at the payload and send it to the path management server. So this is kind of easily done with sort of current means. Now, the second example I want to bring up is a bit of a controversy. So and it's a controversy because I'm going to use the words MPLS in the data center. Okay, I get it, but I'm not telling you to do MPLS in the data center, unless you want to. But I am telling you that there are a couple of good reasons for doing so, and some of them are discussed in this presentation that Yandex did some time ago. But if you did want to do MPLS in the data center, you're likely to want to create packets or craft packets out of your servers that kind of look like this. There's a three MPLS label stack with a depth of 3 labels. And the top label, the orange one, is the one we use to address the Egress top-of-rack switch. The next green label is one that we used that we use to address the actual server or port out of that top-of-rack switch. And then the third label, if you have VMs, that would be the label that would address a particular VM in that server. So by doing an overlay like this, you can actually achieve overlays pretty cheaply. Hesitant to say that you don't need a controller, but you could actually do it without a controller. So the bottom 2 labels are not really a concern for this talk. They usually will get, they'll usually actually get assigned by a controller or an orchestrator in the data center. But the top label is the one we use to do forwarding on. So how do we make the left router, the ingress store, or switch rather, how do we make that ingress store act on that label? If we want to inject that packet from the server, how do we make the server know that label? Those are all good questions, and they have pretty much 3 conceivable answers. One is this segment routing concept of a node SID. It lends itself quite nicely to this. All the egress store needs to do is simply announce a node SID for itself, and then everybody can use that node SID, and we have predictable way of addressing Tor3. Tor3 is the node SID for Tor3. Okay? The only problem with that is you got to upgrade your data center to Spring, to segment routing type of technology. You could go the traditional way and simply create an RSVP LSP mesh in your data center. You will achieve reachability. You will not achieve predictable label values because every, they're going to be dependent on what RSVP assigned for you. Which brings us to the third approach, which is let's use static LSPs with some pixie dust to achieve this label forwarding, yet have very predictable label values for the destination. So what we do also is we enable some sort of a label protocol within the data center, but we don't do a full mesh out of it between all of our egress stores. Instead, we do hop by hop label allocations. So in this example, the Egress store uses BGP labeled unicast to announce its loopback address to its upstream switch. Then it uses BGP labeled unicast to announce that loopback address to everybody else that's a neighbor of his. So eventually the Ingress store gets a label allocation for that 3.3.3.3 address, which is nice, but we can't know what that label is. It's not predictable. It's up to BGP label unicast to announce it. We haven't achieved our kind of main goal here to have predictable label allocations. So the way we do that is by having an extra configuration with a static LSP that says, so this configuration pretty much says, hey, if you should get a packet with a label of 1,000,003, forward that packet to this node 3333, that's the Egress store. So forward that packet there and stitch it to whatever label path is available to you to forward it. In this case, the label path that's available to me came from BGP labeled unicast, and it has a label of something there, which I don't really care about, because this config caused this forwarding state to get installed in top of rack 1. This forwarding state pretty much says incoming label 1,000,003 gets swapped to label 299 something something, which came from BGP labeled unicast. Now, once I do that, I have a way of addressing this egress top of rack switch by crafting a packet just like this one. The top label of the packet is 1,000,003, and every Ingress store in this data center can just generate that one packet, or every server rather can generate that packet. I know that label 1,000,003 will get me to Egress store 3, and I don't have to care what the underlying label distribution protocol assignments were. So in the eyes of a server, this now looks a lot like a node SID. It's predictable, and it's allowing you to reach the Egress store with whatever path is available to you. By the way, these terms spring spirations, I got to credit my friend Steve Woolrich, who is somewhere in the audience there. If you guys like the term, tell me. If you hate it, tell him. So the last thing I want to talk about is the last example is this case for egress peer engineering. That's the last spring spiration, and it's not a spring spiration at all. It has been around for years before Spring was conceived. In fact, the first reference I could find for it is from 5 years ago, coming out of this forum. Tom and Richard kind of explained that sort of the initial concepts around this egress peer engineering, which are, hey, let's bypass the forwarding decision made in our peering routers. And the reason we want to do that is because we want to override the BGP best path selection with something that we think is better. So the way Spring would do that, and again, that's kind of described in details in this purpose-built draft. Spring would assign, Spring, in this kind of solution, you have three main components: the peering router, the controller, and the ingress. So most of the functionality is in the peering router. The peering router would use Spring to allocate segments to these peers. There's going to be individual, unique segments to each peer. Those things are going to get announced to the controller. The controller is going to make its best path selection, and it's going to impose that best path selection on the ingress of the traffic, either host or ingress router. And the end result of that whole thing is going to be that I can create this steering policy that in this example allows me to split that prefix A/8, for example, into 2/16s and send them different ways. and also dictate where B/24 is going to go and C/20 is going to go. Same thing can be done and has been done with BGP labeled unicast. The same concept remains, just the protocol changes. BGP labeled unicast, along with an IGP perhaps, is used to announce these unique labels pointing to peers, and the controller basically gets the same amount of information that allows it to impose the same type of policy on the ingress of the traffic, except this time the policy looks a little differently. Instead of a node segment on the top, you'll have an LSP label. In fact, the interest in this use case from Spring has resulted in a lot of enhancements that we got asked by customers, mainly in two areas. One is to auto-generate these BGP-LE routes representing peers, and the other one is to provide protection for that traffic that is now labeled, so that we don't have to wait for the controller to notice any failures and react to them. So this is just a config snippet of how you do these things. Spring has sparked people's imagination around ideas of an old technology, source routing. It has given them some insights that allowed them to just take a second look at existing problems and solve them with some present existing solutions without having to upgrade their network to Spring-capable code and routers. I kind of covered 3 of those. Hopefully they were kind of meaningful to you and useful, and if you guys want to talk about them, I'll be happy to discuss in the break. Do we have time for question, or I'm done with that?
Thanks, Nick.